Okay, and then I will just share my screen. So today I haven't been able to put them on slides. So we will just go ahead and do this. Okay, so let's start off with the recap. Okay, and in our recap, just one second, there are some people who have come into the waiting room. I will just admit these people. Okay, all right. Okay, so we will start off with the um, unitary transformations, because I had promised you that I will do a recap of this in this particular class. So I will just do it in matrix representation, right? And if you remember, how had we started off this whole thing? So if you remember, what unitary transformations do is that it takes you from one representation to another um, I will say alternate but equivalent. Okay, so what do I mean by that? I mean that essentially it is a completely alternate, a different kind of way of looking at the whole thing, but um, it is the physics has not changed. Okay, so alternate but equivalent. All right, and these two are being connected by a unitary transformation, which I will put as U. All right, and how basically does it work? If you remember that here you had a set of eigenkets, okay, which were the basis set. Just one second. I have to admit a few more people. Okay. And here, on the other hand, you had another set of eigenkets. Okay. And it's the relation between these two sets of eigenkets that essentially determines what your U is. Okay. Now, what do we know about these eigenkets? As I said last time, we know that they form an orthonormal set, which means that if you take the inner product like this, you will get a delta ij. Similarly, over here, if you did an inner product between any two different eigenkets or the same eigenket, you would get this. So they are an orthonormal set. Okay, so we write it, the orthonormal set, in a concise way using statements which look like this. All right. Now, just one second, more people to be admitted. I should strongly discourage people from coming in late. Okay. Because this is not like your class, where you can just quietly walk in and sit in the class. I'm having to admit everybody, and it definitely disturbs the flow. All right. So now, what else do we know about this? That they form a complete set. What do we mean by a complete set? That if you pick up any wave function that represents a physical state, or one dynamical state of the system, then it can be written as a linear combination of these eigenkets, right? So how do we write it? We write it using the closure relation, and that looks something like this. With this, please remember, this quantity here is the identity, right? And similarly, we can write it for the other state. That is that you can have your phi I, and this is equal to, again, the identity, right? So this is what we know about the two representations. One more person to admit, just hang on. Yeah. Now, what we essentially figured out last time is that we represent if U is your unitary operator, which is such that you can essentially go from representation 1, where your wave function, so let me write it again, we write it as a psi, we write it as x, and operators we write it as a. Okay, and here what do you write? Equivalently, you write a psi prime, you write an x prime, and you write a prime. And what we do know is that, so let me just cancel this. We know that psi prime is equal to u psi. We know that x prime is equal to u x. And we know that a prime is nothing but U dagger, right? Yeah. So then this matrix that is representing the unitary operator, which can do all these things, okay, which can do all these things, how do you represent it? So I will just write down the expression. It is essentially, you write your UJN. I may have used MN or something like that, but not a problem. You know it what it means. And this is defined as the inner product between phi j and this psi n. Okay, yeah, phi j and psi n. So please note how these two link up with the subscript. Okay, now given this definition, what were we able to prove? The first thing we were able to prove, that given this definition, that U is unitary. We proved this, right? Yeah, we were able to do this. The second thing that we did, so let me just look up what we did last class. Yeah, then we also were able to prove that using this, yeah, that it is unitary. Then also that we can write your psi prime equal to U psi. How did we do this? We showed that if there was a column matrix that represent this, okay, which we called as C prime, okay, and there was a column matrix that represented this, which we called as C, okay, then basically C prime was equal to UC, correct? This is what we could prove. And how do you actually write it down? If you have Ci prime is equal to summation over M UIM CM. Where what are these Ci primes? They are components of this and they represent psi prime. And CMs are what? They are components of this matrix and they represent psi. Okay. So this is the second thing that we could prove. We could also prove that in this matrix representation, that your A prime is equal to UAU dagger. All right. Now, what was a very, very important thing that we could prove additionally? Okay, we proved, if you remember, let me just make the steps that, yeah, first thing that you should remember is that if, so let me just note down the points which went into this last proof. One is that Hermitian matrices, Hermitian, okay, I think I'm run out of refill. Hermitian matrices, okay, can be diagonalized. This we didn't prove over here, this we already knew. Can be diagonalized by unitary transformations. Okay. What was a second thing that was very, very important in this proof? Just one second. There are a few more people who have come in. Let me just admit them all. Yeah. So what was the other thing that we learned in this particular, yeah, we learned that if you use the eigenkets of an observable as a basis. So this is not over here, but we learned it earlier, okay, as a basis, then the observable is a, what kind of matrix? It's a diagonal matrix, right? It's a diagonal matrix. Not only that, diagonal elements are eigenvalues, right? They are the eigenvalues of that particular observable, right? Now I'm going to change page. Just remind me to change it on the iScribe as well. Yeah, change it. There are 3 more people in the waiting room. Let us admit them all. Some people seem to be having to rejoin. Okay. My sympathies for that. Yeah. So, and then what does it further we know? We know that the trace of the matrix in such a representation is the sum of the eigenvalues. Correct? So this is what we know. And what did we end up proving over here? If you remember, we ended up proving, okay, that unitary transformations do not change the trace of a matrix. Okay, so this is what we proved over here. And if we put all the information that we have put down so far, the few points that I put earlier and this particular statement, what does it tell us? It tells us that the trace of a Hermitian matrix is always the sum of its eigenvalues. Right? So this is a very, very important theorem, and I hope you will remember it. Okay? The trace of a Hermitian matrix is always the sum of its eigenvalues. So please remember again, what was the logic? Any Hermitian matrix can be diagonalized by unitary transformation. When a matrix is in its diagonal form, that will happen when it's using its own eigenkets as a basis set. The eigenvalues form the diagonal elements. So the trace, which is the sum of the diagonal elements, forms the becomes the sum of the eigenvalues. Right? Now, we hear that from unitary transformations will not alter the trace of a matrix. So thereby, for a Hermitian matrix, okay, the trace is always the sum of the eigenvalues. I hope this is completely clear to everybody. Okay. So if there are any doubts, I'm going to just stop the share briefly, because after this, I'm going to start recapping the simple harmonic oscillator. If there are any doubts, please just tell me right away so that we can then move on to the simple harmonic oscillator. Any doubts, please? Does anybody have any doubts? When they looked through these notes, you found that there was something that was not evident to you, you can please tell me right away. Any problems? Was everybody good with this? Yes? No answers. Nobody has read up their notes or what? Yamini, did you understand this? Yamini is just logged in and gone off to sleep or what? Yamini, are you there? I can see that little box which is marked Yamini R. Are you there? Okay, Pragnya, what about you? Did you understand? Yeah, hi, Yamini.
Yes.
You understood? Good. What about you, Pragnya?
Yes, ma'am.
Okay, good. Just tell me, okay, if you have doubts. Fine. So let's get back now and we will just recap what we did with the simple harmonic oscillator. Okay, so I will assume that we all know what has been happening with the, what do you call it? Let me just share and then talk. Yeah, we have understood what is happening with unitary transformations in matrix representation. We already know about unitary transformation, but this was the matrix representation where we had this additional new information that came up for us, which is that the trace of the Hermitian matrix is always the sum of its eigenvalues. Or we know that unitary transformations do not change the trace of a matrix. Right. Now we come to the linear harmonic oscillator, and as I told you, this is a way of demonstrating for you that there can be alternate ways of solving for the eigenvalues and eigenstates. Actually, you can use this method also for solving for the eigenstates of a physical system. And the physical system to point is the linear one dimensional harmonic oscillator. So I will start off with just writing down the, so please remember here the potential is time independent. So we are only worried about trying to solve the time independent Schrodinger equation. Okay, time independent potential, right? So how do we write down the Hamiltonian? The Hamiltonian is nothing but your, so we write it down in the special form. If you remember, we have an h cross omega by 2, which is taken outside. It may look a little confusing right now, but just go with it. Okay. And then we have essentially px square by m h cross omega. This is, of course, your linear momentum operator in the x dimension. And then over here, we have an m omega by h cross, and then we have an x square. All right, so this is your Hamiltonian. And what we do is that we introduce two new operators, an a plus and an a minus. I kind of justified it for you in the last few classes. So let me just remove some pages from here and then just look up my notes. I always get these things a bit wrong if I don't look at them. So it is essentially 1 by root 2. And then we have an m omega by h cross power half x. And then we have a minus I 1 upon m h cross omega power half px. Okay, so this is essentially your a plus operator, and then we essentially had your a minus operator, which is m omega by h cross half x plus I 1 upon m h cross omega power half px, right? Now, what did we do in the last class? If you remember, our basic idea was to understand these two new operators, what they do, and why it helps us. Okay, so what we did first of all is that we realized for ourselves that a plus and a minus are not Hermitian. Okay, so this is important because you also need to know that it is not all operators are Hermitian, definitely. And remember, it's not just Hermitian operators that are important for us. There are other operators also that can be important for us. And A plus and A minus are operators which can be, what do you call it? They are, examples to put up for that. Okay, that even operators which are not Hermitian can be useful. Now, what do we know in this? That A plus dagger is nothing but A minus and vice versa. Okay, this, so you just take daggers on both sides and you will prove that A minus dagger is A plus, right? Then the second thing that we did last time was we worked out the commutator relation between A minus and A plus. And what did you find? It's a very, very important relation. I have always told you that commutator relations are extremely important. We found that A minus A plus commutator was 1. I hope that derivation was very clear. And what did we utilize? It was very important. We utilized the commutator relation between x and px, and we knew that was IH cross. We used this to prove that the commutator between A minus A plus is 1. So remember, the commutation relation between x and px is actually now getting pulled into this commutation relation between A minus and A plus equal to 1, which is a simpler looking relation, if you please. Now, what did we do? Using this, we actually wrote down the Hamiltonian using just either a minus a plus. Okay, that reminds me. Let me go back here and write down how you write the Hamiltonian in terms of a minus a plus and a plus a minus. Wrong of me to have walked away from that. So we wrote the Hamiltonian down as h cross omega by 2 into a plus a minus plus a minus a plus. Okay, so this is what we had done once we cast it in terms of this a plus and this a minus. Okay, now what do? We write down the Hamiltonian again only in terms of a plus a minus or in terms of a minus a plus. And what were the relations that we got? We could write, I think, the Hamiltonian equal to, just let me write down the final relation. I don't want to waste your time by deriving it again. You could write it as a minus a plus minus half. Okay, I hope I've written it correctly. And in terms of a plus a minus, you could write it as h cross omega a plus a minus plus half. Okay, so I hope this is correct. And then remember that I told you you can define your a plus a minus as a new operator, which is also called the number operator, and you could write your Hamiltonian h as equal to h cross omega into n operator plus half. You'll see the significance of that a little later. So somebody has entered the waiting room. Let me just admit the person in. Yeah. And now, what did we do after this? If you remember, we worked out, I said commutator relations are extremely important. So we worked out the commutator relations between H and A minus, right? And what did we get for this? If I think we had finished this last time, we got it as, had I finished this last time? The commutator relation between
Yes,
H and A?
ma'am.
Yeah, okay. So this was nothing but minus H cross omega A minus, right? And we also did the commutator relation between H and A plus. And here we got H cross omega A plus, if I'm not mistaken. Yeah. Okay. So this was where I think we were. I had gone one step further, but I will start today's class, the fresh stuff from this point onwards. So are there any doubts? Okay. Any doubts in the commutator relations that we derived and so on and so forth? If there are any doubts, just tell me and then we shall move on. So any doubts, please? Has everybody understood everything about the linear harmonic oscillator, what I have said so far? Any doubts? You should see the logic in which the math has been developed. Okay, yeah, and then you should realize that this math has been developed so that it makes the solution of this problem easier. Meera ma'am will be solving the linear harmonic oscillator by just solving the differential equation, which is the Schrodinger equation. Okay, and you will realize that solving that differential equation is way tougher than what we are doing here. Okay, this is a much more simple, much more elegant method, but here you have to understand the logic behind the mathematical steps that we have developed. So any doubts, please? Is everybody okay? Asma, are you all right
Yes,
with
ma'am.
this? All good?
Yes.
Yeah, who else talked to me? I think Supriya, was it? Yeah. Okay, good. So everybody is okay with this, I hope. Then we will continue. All right. Okay, so let's move on to a new step now. All right, so I will go back and share my screen with you. Okay, so let me just change pages once again. Yeah, I keep forgetting to change pages here. All right. So now what was our idea? Okay, so our idea was that, look, we are finally trying to solve the, what is the Schrodinger equation? If you remember, the Schrodinger equation in its time independent form is what? is nothing but an eigenvalue equation for the Hamiltonian, right? Okay, it's nothing but an eigenvalue equation for the Hamiltonian. So what is it? It's essentially you are trying to solve this. Okay, I had written it up for you last time. Okay, where please think about it. This E, okay, is an eigenstate of the Hamiltonian. Okay, this E is an eigenstate of the Hamiltonian, and this is just a number. Okay, this is an energy eigenvalue. Okay, and what we need to find out is what is this A plus going to do to this E. Okay, what does it do? All right, similarly we need to find out what this A minus does to this E. So in order to find out what it is doing, what we need to do is to operate this Hamiltonian on this A plus. Okay, because we will not be able to figure out the action of A plus on the energy eigenstate. We can just do it, the operation, and but we don't know what it has done. In order to know what it has done, we need to extract information from it. What is the easiest information that we can understand? It is the Hamiltonian. So we can see whether this A plus acting on this E has made any change to the energy state. Has it done something? Okay, only from the information that the Hamiltonian can extract from for us, we will be able to understand. And of course it is important that this A plus E, it depends on whether it is still an eigenstate of the Hamiltonian, or has it changed into something which is no longer an eigenstate of the Hamiltonian, in which case the information extraction becomes a bit tough. Okay, so let us see what this uh, H A plus does. All right, so now so this is something that we are going to work out today. All right, so what do we have to do? We have to basically do this. Okay, I'm just repeating that earlier step, which is nothing but HA plus acting on E. Now we know something about the commutation relation between H and A plus, right? I just wrote it up in the earlier page. And what was this? This was nothing but plus H cross omega A plus, right? You remember this? I just wrote it in the earlier page. So what does this mean? It means that HA plus minus A plus H is equal to H cross omega A plus. Correct? So this implies that your H A plus, okay, is equal to, sorry, I'm going to take this term to the other side. Okay, this term which is on the LHS, I'm going to take it to the RHS, the right hand side. So what will I have now? I'll have A plus H, okay, plus H cross omega A plus. I hope everybody has understood this. Okay, everybody okay? I've just written out the commutation relation and written up a new expression for HA plus. Okay, so now let us take this new expression for HA plus and we will put it over here in this equation. All right, so what do we have now? We have H acting on A plus E, correct, which we had written as H A plus E, and instead of H A plus, now I'm going to write down this expression here, which is A plus H cross omega A plus acting on E. Okay, this is what we are going to get. So let's write this down now. So this is an addition of, this one is an addition of two operators. One is this and one is this. And you know how we can write it now? We can write this as A plus H acting on E plus H cross omega A plus acting on E. Correct? Now, what is H acting on E? Please have a look at this equation here, right at the top of the page. Okay, I pointed an arrow to it. So I know that H acting on E, the Hamiltonian acting on E, will give me a number times that same eigenstate. And what is that number? It's nothing but the energy, right? So I will get A plus E, E plus H cross omega A plus E, right? So now let's rewrite it. This is just a number, correct? So I'm going to take it out and write it as E into A plus of E plus H cross omega A plus of E. I can further simplify this and write it as E plus H cross omega A plus E. Okay, right. So now please, so I'm going to write down the LHS down here. So now please pay attention to this. The Hamiltonian acts upon this wave function A plus of E. And what does it give you? It gives you a number, which is E, the original energy, plus H cross omega into the same wave function A plus of E. What does it tell us? It tells us that A plus E is an eigenfunction of H. Everybody agrees with me? It's still an eigenfunction of H. And eigen E plus H cross omega is the new eigenvalue. Actually, maybe we should not say new. Let's cancel that. We'll just call it the eigenvalue. Okay, it is the eigenvalue. So, let us now think about what this A plus did to this eigenstate E. Originally, the energy was just E. Now, what is the energy? E plus H cross omega. So, what has this A plus done? It has changed the energy level, right? Originally, the energy level was such that it gave you an energy of E. But now, with the action of A plus, you have gone to an energy level where the energy is E plus how much? The step size is H cross omega. Now, since the A plus has increased, has made you go up the energy ladder. Remember, it has not increased the energy. It has changed the energy level. It has changed the energy level to something which has an energy, extra energy of H cross omega compared to the earlier energy level. Okay. So essentially, you had an energy level which is of E. Now you have gone to this energy level. Okay, you've gone up with the action of A plus, and this has an energy of E plus H cross omega. All right. So is this clear to everybody? Does anybody have any doubts with what I have said right now? Because this is the crux of the whole thing. Any doubts, please? Any doubts? Either you have doubts or you don't have doubts. If you have doubts, please tell me. If you don't have doubts, say no, ma'am, we don't have doubts. What happened? Everybody's very tired. Yes, Tejashri.
Ma'am,
Yes, please.
this is Naina, ma'am.
Sorry?
Hello.
Yeah.
This is Naina, ma'am.
Yeah, Naina, go on.
Ma'am, Yeah, yes, ma'am. You said there is no increase of energy. It's a change in the energy. So what do you mean by that, ma'am? Means A plus is an increase of energy only, no?
No,
So how
it's not.
you like?
No, no,
What
no,
is the
it's
difference
not.
between
Please
change and
remember, it's not that A plus is putting energy into the system. Okay? The system has different energy
yes, ma'am.
levels. Okay? So what it has done is it has changed the energy level. Okay? So please understand, it's not that
Hmm.
you're going to get increase of energy. So remember, this is finally a physical system. Okay? It has a certain energy, it is going to be
Yes.
fixed to that. If you apply A plus, you
Hmm.
are essentially changing the energy level. Okay, so that doesn't mean that you had a system which started off with energy E, and by applying this operator A plus, you have artificially increased the energy. You cannot do that. Energy conservation will be what do you call it, it will be essentially violated. Okay, so that is what I meant, that this is not a way of increasing energy of the system, but this is a way of you exploring different energy levels of the system. Okay, yeah. So basically
Okay.
why
Okay.
are we doing this? To solve the problem. Okay, the idea is to get all the possible energy eigenvalues of the system. Right. So this is a way of solving for the energy eigenvalues. You're trying to see what energy eigenvalues are possible. So what did you realize now? That if E is an eigenvalue of the energy, then E plus h cross omega is also an eigenvalue. Then if you apply A plus to that again, you will realize that E plus 2h cross omega is also an eigenvalue. Okay, so this is what I'm trying to say. See, this is a very important point that Nayana raised. So let me just get back to the ice scribe. I will tell you exactly what I meant. Okay, see, what we are trying to do is that we are trying to solve this particular equation. Okay, right at the top of your page, we are trying to solve this. Okay, now there are two arrows which are pointing to it. Okay, we are trying to solve the Hamiltonian acting on an energy eigenstate gives you a number, okay, times that same energy eigenstate. So remember, this is just an equation. We don't know this, we don't know this either. Correct, we are trying to solve for it. Yeah, the A plus and the A
Yes, ma'am.
minus are going to help you solve for it. So what you have realized is that, look, if I somehow come up with this value E, okay, as my answer, then what I am realizing now with this A plus is that then E plus h cross omega is also an eigenvalue. Now what I can do, I can again act an A plus on this level. Okay, and I will get E plus 2h cross omega. Okay, I will get a new level. That is
Yes, ma'am.
also an eigenvalue. Correct? Then I can go up again
Yes,
by
ma'am.
an A plus operation. I will get a new level. That will be E plus 3h cross omega. That is also an eigenvalue. Okay, so what I'm trying to say is that A plus and A minus, okay, I've not yet shown you the action of A minus, but A plus and A minus are operators which are going to help you solve this equation on the top. Okay, this equation here, I put an arrow now from the other side. Okay, and what it has helped you understand is that, suppose now I managed to solve it and I have gotten this E as an eigenvalue, then I automatically know, because of the action of A plus, that I can have E plus h cross omega as an eigenvalue. I can have E plus 2h cross omega as an eigenvalue. I can have E plus 3h cross omega as an eigenvalue. I can have E plus nh cross omega as an eigenvalue. In fact, what you should realize is that there is no upper limit. I can keep on climbing. All right. So since this A plus is helping you move up in the energy levels, okay, it is called a raising operator. I told you, right? I will justify this term raising operator. So it's a ladder operator which only makes you go up. Okay. So it is a raising operator. Let me write it down here. It's a raising operator. But remember, this is, it is solving the equation, and helping you. Just 1 second, I need to just cut off this call. Okay. So essentially what I want you to remember is that if you are given a system with a particular energy, you can't say, oh, I want this energy increase, so let me just operate A plus on it. That's not going to happen. Okay. This is basically solving the Schrodinger equation for you, and it is giving you the possible eigenvalues. So it is not pumping energy into the system. Please remember, it is only telling you that if E is an eigenvalue, E plus H cross omega is an eigenvalue, E plus 2H cross omega is also an eigenvalue, E plus 3H cross omega is also an eigenvalue, and you can just keep continuing like this. Is this clear? Is this doubt cleared?
Yes, ma'am.
Okay, good. Any other doubts, please?
Excuse me, ma'am.
Yeah, please tell me.
Excuse me, ma'am.
Yeah, please
Ma'am, we
go
have
ahead.
written value for H as H is equals to H bar omega n cap plus of
H is equal to
previous
which
phase,
step,
ma'am.
please? 1 second. Just say it again.
H is equals to H cross omega
Where have I written this?
previous phase, ma'am.
Previous page. Okay, so let's go to the
We
previous.
have written values for H now, ma'am.
Just 1 second. It's not loading fully. Yeah, I'm sorry. For some reason, it's not loading. This happens at times. So just say it to me. I will write it down. H as in you mean the Hamiltonian, is it?
Yes, ma'am.
Yeah. H is equal to,
Yes, ma'am.
yeah, H is equal to
H bar omega
H cross.
H cross omega
Hmm. What?
upon n cap plus of
N cap.
upon into H cross omega into n cap, ma'am.
Huh.
N cap.
Yeah. N cap plus half. Yeah.
N cap plus of.
Yeah. So what is your confusion with regards to
And
that?
other value for H.
Sorry.
No, ma'am. We took where n is equals to a plus and a minus.
Correct.
Where n cap value is a plus and a minus.
It's not value. It's the operator definition.
Why not?
This is a definition. All right. Now go on. Tell me.
Why not for a minus and a plus, ma'am?
Okay, this you will realize as we go along. Okay, why this n has, you can call the other one also as an n cap. Okay, not an n cap, an m cap or a k cap or a q cap. Okay, it doesn't matter. What you will find is that this a plus a minus has a special significance. So please wait. That's what I will tell you. Okay, so yes, you are right. I didn't, I'm being partial here. I'm giving a special name to this a plus a minus, and I'm ignoring the a minus a plus. But there is a reason for that. Okay, and you will see why. All right, just wait.
Okay, ma'am.
Okay, fine.
Okay, ma'am.
So everybody is
Okay.
clear about the action of a plus, right? Any more doubts? Any more doubts? I have to still answer Tejashri's question, but if anybody else has any other doubts, please ask. Okay, silence as usual. Okay, I'll assume that everybody has understood, and we will go on to seeing the action of A minus. Okay, so we will do it pretty much the same way. I'm going to change the page now. Okay, so let us now see the action of H on A minus E. Okay, so this is what we need to find out. Okay, now naturally, as you can see from, taking clues from the earlier one, here we are going to use the commutation relation between H and A minus, right? So let us just write it down. Your H A, sorry, my bad, H A minus commutator is what? We learned that this was nothing but minus H cross omega A minus, correct? Minus H cross omega A minus, which implies that H A minus minus A minus H is equal to H cross omega A minus, which implies that H A minus can be written as A minus H minus H cross omega A minus. Okay, so this I hope is clear to everybody. Now, we want to find out what is the action of A minus on E, and this we do by trying to extract the energy information from the new wave function that has been created. What is the new wave function that has been created? A minus acting on the eigenstate of the Hamiltonian. Then we operate the Hamiltonian again and find out what has been the action. So this is nothing but H A minus acting on E, and instead of this HA minus, now I'm going to put in this expression. So what is this expression? This is A minus H minus H cross omega A minus acting on E. So we can write this as A minus H acting on E minus H cross omega A minus acting on E. Right? So this is going to be now A minus, and we know this is nothing but E, correct? Where this E over here is a number, it represents the energy, correct? Minus H cross omega A minus E. So then we know this E is just a number, so we can write it as E A minus E minus H cross omega A minus E. So therefore we have E minus H cross omega A minus this, right? So let's now write down the LHS over here. H acting on A minus E gives me this number acting on the same function. Okay, so this implies what? That A minus E is also an eigenstate of the system and E minus H cross is the energy eigenvalue. Okay, now
Excuse me, ma'am.
yeah, somebody had a doubt? I heard.
Yes, ma'am.
Yeah, go on, tell me.
Ma'am, is there any difference between eigenfunction and eigenstate, ma'am?
No. No. Okay, I'm using them interchangeably. Yes, eigenfunction, eigenstate, eigenket over here means the same thing. Okay, I'm sorry if I kind of have been jumping
Yes,
around, but don't get confused. Okay, it means the same thing. It means that operator acting on that gives you a number times that same eigenfunction, eigenstate, eigenket. Okay, is that clear?
Yes, ma'am. Yes, ma'am.
So please, okay, in your head,
Yes, ma'am.
eigenfunction, same thing as eigenstate, same thing as eigenket over here. Yes? Yeah, I'm sorry if that caused confusion. All right. So now, what do we realize? Exactly like what we had seen in the case of A plus, now we realize that if E is an eigenvalue, E minus H cross omega is also an eigenvalue. E minus 2H cross omega should also be an eigenvalue, right? Because what is happening now, you're starting off at an energy level E. You act with A minus. You're going to get now a new level where the eigenvalue is E minus, sorry, oh God, E minus H cross omega. You act with A minus again, you get a new energy level, and here now the eigenvalue is E minus 2H cross omega. Okay, and then you can go to E minus 3H cross omega, and so on and so forth. Now, I hope everybody has understood this in analogy of what we did with A plus. Okay? That if you have E as an energy eigenvalue, with A plus you saw that E plus H cross omega is also an eigenvalue. E plus 2H cross omega is also an eigenvalue. And with A minus, you saw E minus H cross omega is also an eigenvalue. E minus 2H cross omega is also an eigenvalue. So now let's just have a look at the whole situation. So we have E. We know E is an energy eigenvalue. Immediately we know that E plus H cross omega is also an eigenvalue. We know that E plus 2H cross omega is also an eigenvalue. And these are all the eigenstates. Okay. If this is E, then you have climbed to some other state over here. We will name it as we go along. Here you have climbed to another state. Okay. And then with A minus, and you can keep going. Right. And then with A minus, what did we realize? That we can also go to E minus H cross omega. And then we can go to E minus 2H cross omega. And then we can go to E minus 3H cross omega. Okay. Now what I want to ask you is that can we keep going down like this all the time? Okay. So what you realize is that what is the step size here, please? It's H cross omega. Correct? Every time it is H cross omega. A plus makes you go up. Right? Okay. So A plus is a raising operator. What does A minus do? A minus makes you come down. So A minus is a lowering operator. Okay. A minus is a lowering operator. Correct? So now the question is, okay, I'm basically using these to go up and down this ladder. You realize that this looks like a ladder, right? What kind of a ladder is it? It is an energy eigenstate ladder. Okay, it's a special ladder. It's, I will say, it's an energy eigenstate ladder.
Ma'am?
Yes, go on, please.
Ma'am?
Yeah, go on. Ask me.
What if it goes from E minus to
What it
yeah?
goes.
What if
goes
it
huh.
goes from E minus to H cross omega to E minus H cross omega, ma'am?
I don't understand you exactly.
Like upwards.
Huh? So you mean to say you can go from here to
Like you
here?
told, if it
Okay. I can do an A minus operation and come here.
in the same way.
And then if I do an A plus operation, I will go
Okay.
back to the same thing. Correct? What did
Oh.
you mean exactly? Can you
Okay, ma'am. Like I asked, if what if it goes from my E minus to H cross omega to E minus H cross omega?
Yeah, you can go. So you are saying you're starting off at this, right? E minus 2H cross omega. You can do an A plus
Yeah.
operation and it will go to E minus omega, H cross omega. No problems. Either way, you can go up and down. It doesn't matter which state you're starting with. Okay? Yeah. But what I'm just trying to tell you is that the moment you know that E is an eigenvalue, you know that E plus H cross omega is also an eigenvalue. E plus 2H cross omega is also an eigenvalue. Also, you can lower. But my question is that, is lowering as simple as raising?
Okay.
Okay. Have you gotten my answer? Did you get, is your doubt cleared?
Okay.
You don't sound
Yes,
very
yes, ma'am.
satisfied.
Yes, ma'am.
What is the problem? Tell me. See, you can start at any energy value. Okay?
No, ma'am, I got it.
You got it, right? Okay.
Nothing.
Good. If you have doubts, please ask. Okay.
Yes, ma'am.
I'm willing to clear
Yeah,
out
ma'am.
your doubts. Okay.
Thank-
Please. Okay. Right.
Yes, ma'am.
So okay, so let me just now stop the share. Okay. And let me just try and talk to you about this. You have understood that there is an energy ladder, correct? The A plus makes you climb the ladder. The A minus makes you climb down the ladder. Now, my question to you all is that, can I keep climbing down indefinitely? What does indefinitely mean? Without any limit. What do you think? Is there any guesses?
Ma'am, IH cross.
Sorry? Yeah, Kiran, tell me.
Ma'am, we can go up to IH cross,
You
ma'am.
can
That's
go up to what?
I think.
You're talking about going up, or you're talking about going down?
Yes.
Up, actually, there is no problem. You can keep going up. But what about going down? What do you think? We can go down to what did you say?
I don't think we can.
Pragnya says that we can't keep going down indefinitely. How many of you agree with her? Do people agree with her that you can't keep going down all the way?
Yes, ma'am. The system might have a minimum energy.
Exactly. Very good. Very good. So the system will have, so you know what can be less than zero energy? Let's think, okay? In such a system. It's not a, it's a bound system, yes. But it's like the ladder, okay? You place the ladder on the ground and you climb up. Once you're somewhere in the middle, you can climb up or you can climb down. But once you're on the ground, where will you go? How low can you climb? Okay. So, as Akshaya said, and Pragnya also kind of said it, the system is likely to have a minimum energy. Once you reach that minimum energy, you cannot go down. Okay. So, there is something called as a ground state energy. What is the ground state energy? It is the minimum energy a system can have. Classically, we think of it as zero energy, correct? We can't imagine something, saying a minimum energy, which is not zero energy. All right. So there will be a minimum energy. And here it is like, you have the ladder. And once you keep climb down, you climb onto the ground and then you cannot go down. So that's the ground state. So once you have the ground state, you actually cannot lower anymore. Okay. So how do we tackle this problem mathematically? So what we will do is we will stop the class now. We will meet at 2 and I will take it up then. Okay. So I hope everybody has put in their attendance. Those who haven't, kindly put in the stuff in your chat right now. And I will send you an invitation for the 2 o'clock class. And then we will hammer this thing through. Okay. You will realize that that is, that rule that you put in, that you cannot lower below the ground state energy. Okay. That will actually give you the value of the ground state energy. So it's a very, very elegant and beautiful method to solve the linear harmonic oscillator problem. So has everybody put in the attendance? Can we end the meeting now? I'm going to stop the recording.